Hello everyone, in this lecture we will explain AVR arithmetic operations and the effect on the SREG register. The first instruction we're gonna discuss is ADSC, which will take two registers, two GPRs, and what this does is that it sets the destination register with the addition of these two plus the carry. Remember, the carry is found in SREG, and usually it's a flag. This is the ALU. So when we have this, the ALU, we have the carry flag, the zero flag, the N flag, and so many other flags. So one of the main application of this instruction is in 16-bit addition. You know, AVR at Mega 3 to 8 is 8 bits. This means the ALU can add 8 bits and the result is 8 bits. What if you want to add two 16-bit numbers? So imagine we want to do the addition of 0x3CE7 and 0x3D8D. So typically what we do is we divide them both. We place each 8 bits in a register because the GPR can only hold 8 bits. So let's say we place this and this in a register. So we can place this in R0, this is in R1, this is in R2, and this is in R3. Let's say these registers are already there. So what we do is we do add. So first, to do the 16-bit addition, we need to add the first 8 bits, which are this and this. So we add R3 and R1. So what happens in this operation is that we are saying R3 is equal to R3 plus R1, which means 0xe7 plus 0x8d. Now if we do the addition of these two, so let's say this is E7 and we have D, which is 1, and 8. We have this is 1, this is 0, 1, 0, 1. We notice that the carry is equal 1 after doing this addition. So this carry should be added to the addition of 3C and 3D. In this case, we use add with carry. So ADC, R0, R2, R0. And what this does, it will actually place R2 is equal R2 plus R0 plus carry. In this case, is going to be 3C plus 0x3D plus carry, which is in our case is 1. So we could not have done the 16-bit addition without including the carry from the previous add. Okay, so to recap, we have those two 16-bit numbers. To do the additions, we need to add the two 8-bit numbers on the right, and then add the two 8-bit numbers on the left, and the carry between those two should be included with an ADC instruction. Now, if we took a different case, sub instructions. So when we do subtraction, in AVR, we have several instructions. We have sub rd rr, which does rd is equal rd minus rr. We have sub c, which SBC, which is rd rr is equal to rd minus rr minus c. And we have sub I rdk. This subtracts from a constant. And we have sub ci, which does the same as sub c, but this times from a constant. So subtracts rr from rd, sub c subtracts rr from rd, and it subtracts the carry, which is going to be the borrow, and I will explain this in a bit. So let's take an example. So imagine we have LDI R20 0x23, LDI R21 0x 3f, and now I want to subtract R20 from R21. So what this does is R21 is equal R21 minus R20. If I want to do this manually, so first I'm going to write the 3f, which is going to be 0, 0, 1, 1. And then I'm going to write the R20. Remember, here we're doing 2's complement subtraction. So effectively what we are doing is plus R20 bar plus 1. This is the 2's complement subtraction. So what's the inverse of R20? If we take R20, so minus 0x23. So if we take 0x23, it's going to be 0, 0, 1, 0. We do the complement. This will be 1, 1, 0, 1. There's a 0 here. 1, 1, 0, 0. And then we add 1. The result will be as follows. So we plug this here and we perform the addition. If we do the addition here, it's going to be 0. It's going to be 0, 1. Another one, 0, 0, 0, and the carry will be 1. So if we look here, the number is positive because the most significant bit is 0. So what does carry equal 1 means? As we can notice here, carry equal 1 in our calculation. However, after a subtraction, carry will be inverted and this will turn into 0. So after the subtraction operation, the carry bit is inverted to indicate there is no borrow because we didn't borrow any number. The relationship between carry and borrow is the inverse. So an important note here, after subtraction, carry is inverted. Only in a subtract operation. We see here the carry is equal 1. It is inverted, so there is no carry. And this means, this is because what we mean by carry is the inverse of the borrow. And since we don't have borrow, this means the carry is 0. So if I ask you, after the operation 3f minus 23, what's the carry? It will be 0, which indicating that this is the borrow. Now, if we take another example to illustrate more with the sub C example. So let's say we have this problem. Let's say R26 has the value 0x62, R27 has the value 0x27, let's say we want to do something like this. LDI R28 0x96, LDI R29 0x12. We want to subtract first R26 and R28. Then we're gonna subtract with carry R27 and R29. So at the end, I will tell you what is the value of R27 and the carry bit. So first, let's take this operation. So we have R28, which is 96. So what this does is we have R26 is equal R26 minus R28. So let's place R26, which is 0x62. We're going to subtract this from 0x96. So first, we place this in binary. So 6 is 0110 and 2 is 0010. Now we want to, since this is the subtracted operand, we need to change it to 2's complement. So changing it to 2's complement, we have, this is the number, this is 9 and this is 6. So we do the inverse, the complement. It will be 0110. We add 1 and we will have 1 0 1 0 1 1 0. So we place this. So here now we can add the values. Now if we do the addition, this will be 0. Have 1 here, 1 0 1 1. Okay, so here notice that the carry and my operation is 0. However, as I told you before, this will be inverted, so this will be 1. See, is inverted after sub. This indicates that carry equal 1. So if I ask you what's the carry, you say carry is equal 1, which is indicating that there is that the borrow is actually 1. Now, if I want to do the second line, which is this one, I will do, it's going to be R27 is equal R27 minus R29 minus carry. So if we add this, if we place this, this will be R27 has 0x27, this is R27, R29 is 0x12. So let's change this to 2's complement. So complement, this will be 1110, 1101, add 1. So this will be, okay. So the result of minus 012 is as follows. So let's write 0x27 and then the 12, which is the 2's complement of it. Let's add them together. Okay. And here the result is 0, then 1, and the carry is equal 1. Remember, here the carry will be inverted. So this will be 0. And then we subtract 1 from it. So subtracting 1 from it will be easy now. We just remove this 1. So the result is 0x14, and the carry is equal to 0 because we inverted the carry in this case. So a golden rule to remember that the carry is always inverted after a subtraction operation. Now, after we learned about the addition and subtraction, we're gonna learn about the multiplication operation. So the multiplication operation, of course, when we multiply two 8-bit numbers, so if I have multiplying two 8-bit numbers will lead to a 16-bit result. So I'm going to demonstrate this in a while. So the instruction for multiplication is MUL, takes RD and RR. So what this does is it multiplies RD times RR. However, the result will be 16 bits. So it's going to be, so this is 8 bits and this is 8 bits. So the result will be placed in R0 and R1 by default. So whenever you do this multiplication operation, R0 will have the lower bits and R1 will have the higher bits. So another example is multiply signed, RDRR. It does the same, but this time uses signed numbers. So here, if you have negative numbers, it takes care of the sign. And we have also, if we have one unsigned and another one is signed, we have multiply SU RD RR, and this multiplies unsigned numbers with signed numbers. Okay, I'm gonna go over multiply RDRR. So let's say we have a small program like LDI R23 0x25, LDI R24 0x65, and then multiply R23 R24. So we don't really care about how the multiplication happens. So let's say we have, the result will be, so we have 0010, this is 25, and 0x25 times 0x65, and then we have the result of this multiplication will be as follows. This will be and then we have E and zeros. So the result will be 0x0E9 9. After doing the multiplication, this will be found in R0 and this will be found in R1. These are the lower bits and this is the higher bits. So now I can do any instruction to work out. I can add, if I want to add those numbers, now I have them in R0 and R1. So when multiplying two numbers using AVR microcontroller, the multiplication instruction will store the lower byte in R0 and the higher byte in R1. Now if I want to go over some logical operations, I have the following. I have the AND, takes this value, takes RD and RR. Of course it does. RD is equal RD and RR. It does something called bitwise AND, which is ANDing the two numbers bit by bit. I'm gonna explain this concept later. So OR, also RD, RR, also bitwise OR. We have the XOR, EOR, this is XOR, EOR, RD, RR, does RD. We have the complement, which just flips the bits. It takes just one register, and what it does is it flips the bits. We have also the negative, and this does the 2's complement. So what that does is, so this does the 2's complement. This is just the complement. So let's say I want to do a LDI and AND example. And R17, R16. So now if I want to solve this problem, of course we change to binary. This is 0x25, then I have 0x15. This will be, so if I AND, I take just 2 bits at a time. So 1 and 1 will be 1, 1 and 0 will be 0, this will be 1, this will be 0, 1 and 0 will be 0, 1 and 0 will be 0, and these will be also zeros. So the value here is 0x05. Adding 0x25 and 0x15 will give me the result 0x05. If I want to take negative R17, what this does is it flips the bits first. So we'll have 1, 1, 1, 1, 0, 1, 0, then adds 1, 1. R17 will be equal 0x F, and this will be C. This will be FB. Okay, so AND, OR, and XOR will work as bit by bit, as we explained, and the negative will just flip the bits. Now, if I want to explain some compare instructions, I have CP compare, RD, and RR. So CP means compare. So what this does, it just performs RD minus RR without saving the value of the subtraction. So no saving of subtracted value. So what this does is just subtract these two, and what I gain from it is that I update sreg, specifically C flag and Z flag and N flag. So if the result is 0, or we have a carry, or we have N, also of course it will also update V and S. Okay, so comparing it to these two instructions, for example, I can say LDI R16 0x15, LDI R17 0x05, and I say CP R17 R16. So what this does is R17 minus R16. So in this case, it just does the subtract operation, and these flags are updated. So Also, there is another variant which is CPI, which means compare with a constant. And what this does is I do RD is RD minus K. Okay, so in this case I am comparing with a constant. So these are very useful when we want to do some decisions. So decisions are taken using branch instructions, and I'm going to explain this. So main use is when we are making decisions. If this number is bigger, if this number is smaller, what shall I do? So it's usually coupled with a branch instruction. So let's talk about branching instructions. So imagine that I want to test if a value is 0 and go to that test. So what I want to do is something like this. If R16 is equal R17, okay, output place on port B 1, else port B will be equal to 0. So typically when we want to place something on port B, we use the out instruction. So this will be out instruction. And also this will be out instruction. So here, what we want to do is, first, we want to compare those two. We can do this with a subtract operation, or we can just use the CP instruction. So we can do something like CP R16 R17. So what this does is, actually it subtracts R16 from R17. If the result is 0, implies the 0 bit is equal 1. So now I need to take choice. I need to go to a place where port B, where to set port B, and then I need to if they are equal to 0. If not, I need to go to a place where I need to set port B to 0. So in this case, I use something called branch instruction. Branch if equal, BREQ. And in this case, what I want to do, if the 0 bit is equal to 1, I'm gonna go to on. This is just a label. Else, I need to go to another place, which is off. So if they are equal to on, if it's equal, it's going to go to on. Otherwise, it's not equal. So off will be LDI R18 0x00 and out port B R18. Okay, so on will be as follows. Here we need to jump exit. On LDI R19 0x01 out port B R19, and here is exit. So let's trace this program. So so we compared here. So we compared R16 with R17. So I'm saying if they are equal, we branch here. So what happens is that the program jumps over those three instructions. It will put R19 1 in R19, and then R19 will be placed in port B. So here we have port B equal 1. Now this is the R16 equal R17 and 0 is equal 1. Now, if this was not the case, no branching will take place. We go here, we place 0 in R18, and then port B here will be equal to 0. Okay, now this jump exit is very important. So when I finish if the case where the numbers are not equal, I execute this instruction, then this instruction. If I don't place jump exit here, it will continue on executing LDI and out port B R19. So this instruction will actually jumps into exit. Alright, so let me repeat. So here we have some sort of an if-else condition. So if the numbers are equal, I go to the on label. This is a label, okay? This is a place inside the code. If the result is not true, I go to off by default, because I could have just removed this because there's no place that's calling off. But just for clarity, I put off and on. So if the condition is off, I execute those two instructions and then unconditionally jump to exit. So branch if equal allows me to branch based on a condition. So let me write this. BREQ, and it takes a label. Okay, branch if equal. This means if z equal 1 based on a previous operation, in our case it will be CPR16 R17, go to or jump to a place where label is. So this is label. On is label, we place it on with two dots. So in our case, on is the label and should be some sort of an address in ROM. So effectively, if I place the ROM like this, okay, I have BREQ on, and on should be somewhere that's pointing here. We will discuss later in the next lecture how we will be able to calculate on and how do we change it to binary, so don't worry about that now. So branch of equal, it just changes the course of execution of a program. The normal course of execution is one instruction at a time, but branching, what it does is actually it skips over some instructions. It can skip up, it can go up, or it can go down. So I can do a loop with it, or I can just do a simple if-else. Okay, so we have many different type of branch instruction. I'm gonna do a table with them. So types of branches. So what we have BREQ, branch if equal, the two numbers are equal, BRNE, branch if not equal, in this case z equals 0, in this case z equal 1. We have BRSH, which is branch if same or higher. This condition happens when C is equal to 0. Branch LO, which is branch if lower. This happens when C is equal to 1. We have also branch less than for signed. This happens when if s equal 1, we have branch greater than, this happens when s equals 0, branch vs, branch when overflow, this happens when v equals 0, and brvc, branch if overflow is cleared. Excuse me, should be 1. Branch when overflow equal 1, v equal 1, and the branch if overflow is clear. So I can use all of those instructions to compare, to do different if-else conditions. So the main purpose here is to generate something like an if condition, we execute some instruction, then an else condition, and we execute this instruction. Okay. Give an example about using branch instruction. Assume I have a temperature sensor that's connected to port B. So let's say this is the microcontroller. I have on port B a temperature sensor that's giving me T. This is port B. Now I'm gonna read this temperature and I'm gonna compare it with 75. So if it's equal to 75, R16 will have the temperature and everything will be 0. If it's greater than 75, R17 will have the temperature and the rest is 0. If it's less, this means R18 has the temperature and all the registers are 0. So first, I'm gonna start by clearing the registers. So I can do LDI 0x00 and then place them inside of R16, or I can use a different instruction called the clear. R16, clear R17, and clear R18. And what this instruction does is just place 0 in those 3 registers. Now, after I clear them, I need to read from the port. And as we know, reading from the port is done using an in instruction. So in R20 pin B. So I read into this value. Now I have in R20 the temperature. I need to compare it with 75. I can use the CPI instruction, compare with an immediate, and place R20, 75. Now, here I need to do the decisions. So I'm gonna write the first branch instruction. So I'm gonna first say if it's equal or higher. So I can use BRSH, equal or higher. So if this is true, I'm gonna go to a label, I'm gonna say same or higher. So this is the case where it's greater or equal. Now, if this is not the case, this means I am in the less domain. And what I want to do is, when I'm in the less, I want to do this condition, which is place in R18T, because all the registers are zeros, so now I need to place in R18T. So I do the move instruction, move into R18 the value of R20. So this is the case where T is less than 75. And then I go with jump exit. Now, where exit is somewhere in the code, the end. Now let's say I want to do so let's say I want to continue, and what are the two cases? So the two cases are here, same and high. Okay, so if it is not less, this means it's greater or equal. So now I will test for equal. So I'm gonna do BRNE, branch not equal, higher. So in this case, I'm saying that it is greater because it's not equal to 0. The only case now that's available for me is that it's higher. So if it's not higher, then of course it's equal to 0. This means I'm in this domain where R16 should be equal to 75. So I will do move R16 R20. So this means T equals 75. This is the case where T equal 75 and R16 equal T. Here we have R18 equal T, and of course I do jump exit. The last case I have is at high, where I don't need any branch here because this is the last case. I just do move R17, R20, which means T is greater than 75 and R17 is equal to T, and exit is here, or you can place it here. So if I will do a tracing on this program, so let's say T is equal 85. Okay, so I compared R20 with 75. So if T is greater or equal, then branch SH will go to here. Okay, so this is where T is equal 85. This is the case. So T is equal 85. This is equal or greater. So I'm gonna go there. Now, if it's branch not equal, is 85 equal to 75? This is it's not equal. So this will branch again to here. T not equal 85. And here T is equal to 85, this means it is greater or equal than 75. And I go to this state where R17 is equal to T. Now if I take another case where T is equal, let's say, is equal 65. So T equals 65. This means, is it same or higher than 85? No, it's actually less. So T is less than 65, and this will execute those two instructions and will have R16 equal T. Okay, and if it's equal to 75, then this is where we have the equal part to 75. So if I have T, the third case, equal 75, it will jump here, and then we will finish with T equal 75. So you see here I have some sort of an if-else condition. So I'm saying if I want to write it in C code, I'm saying if T is greater than, if it's less than, or if it's less than 75, else I will do R18 equal T, else if T is equal 75, R16 equal T, else R17 equal T. This is the rough translation in C code of this program. We're gonna go over the rotate and shift operations. Shift operations. So usually we would like the bits to shuffle or to move from left to right. So let's say we have those bits like this. So remember, this is the most significant bits, D7, and this is D6, and we go all the way to D0. What if you want to rotate those bits or shuffle or take them left or right? So this is right and this is left. We have some instruction that does this, and they sometimes use, especially for rotate, they use the carry flag. Okay, so this carry flag will be used when we're going to rotate right or even going to rotate left. The instruction we're talking about is called ROR, or rotate right through carry, and it takes a register RD. So what this does is actually it shifts the bits one time to the right. So what happens is that this register, this C, will go all the way here. So we have the C, the D7 will go there, then we have D6, D5, all the way to this time D1. This is D1. Okay, so and here we have D0. Alright, so before doing a rotate instruction, we need to take care of carry. So we need to clear it or set it. A nice instruction to clear the carry is CLC. Okay, so when we write CLC without no operands, this means C is equal to 0. So initially, when we do this, and carry is equal to 0 based on this instruction. So let's say we have LDI and say R16 0x26. Okay, so let's fill in the bits. This is 0. This is another 0, 1. This is 2, and then we will have 0, 1, 1, 0. Okay, so this is D0 and this is D7. So what happens when we do ROR R16? So effectively, this bit will go there. So the carry will actually be 0, and this 0 will go all over here. So we will have this new 0 in. I'm gonna write it in a new line and a new color. So this is 0 coming from the carry, and then we go over the rest of the, this is D7, D6, and we have 1, 0, 0, and 1, 1. So remember, this is D7 now, this is D6, it's D5, and we go all the way to D1. So what happens if we do another ROR R16? So now the carry will be 1 because this bit goes here, and then we will have 2 zeros that came from carry, and then we have 0, 0, 1, 0, 0, 1. A third ROR R16. So let's call this. Of course, the carry will be 1, and then we will have this carry going over there, 1, 0, 0, and then we left. This is D7 now, and we have this is another 0, 1, 0, 0. So remember, these bits are all going here. Okay, this is what happens when we rotate. So this is rotate right instruction. We also have a rotate left instruction. Okay, so with rotate left, what we do is the same thing, but it's the other way around. So rotate left through carry. It's going to be ROL, and it takes RD. This time I'm going to conveniently place the carry here, and I'm going to say, okay, when we want to rotate left, it's going to be like this. and the bits go over. The carry will enter from the right side as it's rotating left. So just check the flag orientation. So let's say I want to set the flag. So here we use SEC, which means I'm gonna set the flag. Okay, I'm gonna go ahead and place in R16 a value. It's gonna be 0x15 for my example. So 0x115 is 0, 2, 3, and 0, 1, 0, 1. Now I'm gonna say rotate left for R16. So you will notice that what happens is that this 0 will be inside the carry. It's the carry. Okay, and this one will go over here. So what we have is 1 from the carry, and all the bits are shifted like this. So we have 1, 0, 1, 0, 1, 0, 0. Okay, so this is the new value after another rotate. If you do another rotate left, so now the carry also will be 0. Okay, because we're shifting like this, and then we will have a 0 from the previous operation. So this is 0, this is 1, and then we will continue with the bits 1, 0, and then we have also 1, 0, 1, 0. Okay, so this is the value of the next operation. Okay, and we can continue furthermore. Now another operation that will be useful is shifting. Shifting is about throwing bits into the carry without having this rotation. So here we notice that we are rotating. The bits are going from one place and then returning to the other side like so. Okay, so all with the bits are rotating. So what if I want to shift the bits, not actually rotate them? So we have two instructions for these. We have LSL, left shift logical, of course through carry. This is going to be through carry. Okay, so let's say we have LSL RD. So in this case what happens is that this is, I'm shifting left, 0 will go inside. Okay, so I'm always shifting in 0. So if you take an example, let's say I'm gonna do CLC, this means C equals 0. Then I'm gonna go ahead and say LDI R16 0x26, and then I'm gonna do LSL R16. So first the carry is inside 0. I don't care about the carry in this case, and I have 0x26, which is 0, 0, 1, 0. Okay, this is 26. So when I do LSL, a 0 is entered from here, and this will be thrown into carry. So this 0 will go here, and then I will have 0. Let me start from here. 0, 0, 1, 1, 0, 0, 1, 0. Okay, so it's effectively as if I multiplied it by 2. Remember, if I have 1, I shifted one place to the left, it will be 1, 0, this will be 1, this will be 2. Then I shifted again, this will be 4, so as if I'm multiplying by 2. Okay, now in the case of logical shift right, it is the LSR instruction and it takes RD. Same operation as shifting left, but in this case we are shifting zeros into the right side, to the left side going right, and this means that the 0 will go before D7, D7 will be shifted right, D6 all the way to D1, and D0 will be in the carry. Every time we do a logical shift right, a 0 will be fed in. For example, if you do it twice, this will always be 0. Okay, going like this. Now we have 0, 0, D7, D6 all the way to D2, and now I have here D1. After 8 shifts, the value will be 0. Now if I go ahead and take another instruction, which is the arithmetic shift. Arithmetic shift preserves the sign. So if you go ahead and check the arithmetic shift, it's called the ASR. It takes a RD. So here what we have is that the most significant bit, which is D7, will always be fed into the last bit, and of course we're shifting right, so the value goes into carry. Now to take an example, let's say we have LDI R16 0x96. So let's write this. This is 1 0 0 1, and then we have 6 1 1 0 and C. So now when we do an arithmetic shift, this is always being fed. So we first isolate the 7th bit or the 8th bit, D7. This is it. So 1 will always be fed. So when I do ASR R16, what happens is that, of course, 0 will go into carry. Then we have 1 1 0 1 0 0 1, and this one will be regenerated again. So we're always feeding 1. Now if I do another ASR R16, then remember we always have this feeding operation. So this will go into the carry. So 1, and then we have 1 0 1 0 0 1 1 1. Okay, so we're always regenerating the most significant bit. Now if I do it with a value which has 0 as the most significant bit, so let's check this out. $55, for example, and we do an ASR R16. So we have 0 1 0 1. This is 5 5, and this is the carry. So now this 0 will regenerate, and what we will have is that 1 will go here, 0 1 0 1 0 1 0 0. We notice here that we start feeding 1. Again, another ASR R16. In this case, the 1 will be replaced by this 0. And we have 1 0 1 and 0 here, and 1, and we see that the 0 is always being fed. So arithmetic shift right preserves the most significant bit. The reason behind using ASR is to preserve the sign. So here we are preserving the sign of the number. So if it's negative, it will continue being negative here. So this is still negative because the most significant bit is 1. And if it's positive, it will not be distorted and have a negative instead of being a positive. The last instruction I'm going to discuss is a simple instruction. It's called swap, and this will conclude this lecture. So swap operation it takes one register, a single register. So what it does, it just swaps the bits. So let's say this is D7 till D4, and this is D3 till D0. So what after a swap operation, what will happen is that we'll have D3 to D0 here and D7 to D4 here. So let's take an example. LDI R16 0x96 swap R16. So what will happen is that R16 will be 0x69. So initially it was like this 1001. After swap, it will be 0110 and 1001. So this will go like that, and this will go here.